So the goal of Unit 10 focuses around areas between curves. And we do some stuff with the areas between curves in the future lessons, but we just start with the basics of can we find the area between these two curves. Okay? Now, this is different from last unit and 2 units ago. It's more like Unit 7. We could have gone straight from Unit 7 into this unit, but there's other stuff that I'd like to get out of the way before we come back here. So this is why I do this at the end. Okay? Goes back to the basics of why we use integrals, and it's to find areas under curves. So recall Unit 7, I could have asked you this question at the end of Unit 7, and you should have been able to get the question right. Find the area of the region enclosed by y equals 0, y equals x squared, x equals 2, and x equals 0. It's important to know what the region looks like. X equals 0, y equals 0, x equals 2, y equals x squared. Okay? We are talking about this shaded region. Now, please discuss with your neighbors what the area of that shaded region is and how you would find it. Go. What type of mathematical expression could you set up that represents the area, and how do you find the actual area, the exact value? It's funny, we lose kind of touch with the basics of what we've been doing in the second semester with all these applications. Now, some people go back to the first thing that we talked about in Unit 7, which is Riemann sums. But we know that we don't have enough time and enough computational powers with our pens and pencils to do a good enough Riemann sum to get a good enough approximation. Our calculators do, though. Our calculators do use Riemann sums and does a powerful Riemann sum and its computational abilities to quickly get an answer for this area. But we know that we can't do that. Instead, first we understand that an integral can be used to express this shaded region, the exact area. And then we remember that we can use the fundamental theorem of calculus, which states that an area under a curve is just equal to a change in an antiderivative. Just like when we calculate distance, you can use velocity times time, or really speed times time, or you can find the change in your position. Add all your positive displacements. So that's what we do. We're going to find the change in position. We're going to take the antiderivative. Do you need a plus c? No, you don't, because you're finding the change in it, and the plus c's will go away. And you just plug in 2, and you get 8/3, right? That's where integrals came from. Now, after kind of going through the process of Riemann sums and then kind of introducing the integral, most students just translate this immediately. They forget where it comes from. They say, this means area under x squared from 0 to 2. And you're correct. That's what it means. It means area under x squared from 0 to 2. But what's very important for this unit is to understand where it comes from. Okay? And understand that, yes, it can be translated into area, but what it started with was an infinite sum. Okay? So a sum of infinitely many things. And what we're taking an infinite sum of is a bunch of skinny rectangles with a height and a width. Now here's a representative skinny rectangle. The area of this rectangle is a height times a width. The height is given to you by the x squared function. Whatever your y coordinate is on your x squared function, that's the distance from the x-axis to the top of that skinny rectangle. And our width is a very, very small change in x to dx. Okay? We're taking an infinite sum of heights times widths. And we are going to reintroduce ourselves with that rectangle, that representative rectangle, that one rectangle which represents us summing up all of our rectangles starting from here, obviously not with this height, and then going all the way over here, obviously with the height changing. Okay? We're taking an infinite sum of these rectangles going from here to there, right? That's where it comes from. Okay? Now keep that in mind for this lesson, and we'll go back to it in a second. Because if I asked you, can you find the area shaded here in green, most of you will be able to do so because you like to think kind of globally, kind of macro, in a macro sense, and you can say, well, if I look at the area under F and I subtract the area under G, I'll get the area in green, right? Most of you probably would have come up with that easily. If I had the area under F, and I subtract, and in red, the area under G, I get the area in green. But I don't want us to think that way. Rather, I want us to throw down a representative rectangle and think about an expression that can use just one integral where we're taking an infinite sum of these blue rectangles that have a height and a width. Now I'll tell you right now the width is dx, right? It's a very small change in x. But what could be an expression for the height of this blue rectangle? Now I'll give you two numbers maybe to work with. Let's say this y-coordinate, just at this location, we're not talking about in general, but let's just say just at this location. This y-coordinate is 3. And let's say this y-coordinate here is 1. We know the height of this rectangle is 2. All right. Now, what if I moved it to other locations? What would be an expression that could give me the height of that blue rectangle? Discuss with your neighbors. Go, discuss. No matter where that blue rectangle is, what would be an expression for the height of it? Maybe the numbers confuse you. I don't know. If I moved the rectangle, if I move the rectangle over here and gave it the correct height, say it's right here. Okay? I don't know what the y-coordinates are specifically, but I know how I can express this distance. It's this distance from here to here minus this distance right there, right? If I take this and subtract that, I get blue. Good with that? This much minus this much gives us that much. Well, what is that? That's just whatever my y-coordinate is on my top function minus my y-coordinate on my bottom function. My height is this f minus this g. It was 2 in this situation because I used 3 and 1, but it was just really the top function minus the bottom. I'd like us to think about things this way rather than this way. And of course, we're going from A to B. I would like us to think about an infinite sum of rectangles with a height and a width. The width is a small change in x. dx doesn't mean with respect to x. When we're talking about a definite integral, it just means a very small change in x, infinitely small change in x. Okay? So, micro levels. Height times width. Okay, leave some space. We'll come back to this page. Now, let's move our region around. This same region, now expressed by P and M, no longer F and G, is below the x-axis. Now, if I asked you what type of value the integral from A to B of P of x dx was, discuss with your neighbor what you would say it is. What would be the integral from A to B of P of x dx? Is it like a positive? Is it 0? Is it a negative? Do we not know if it's positive, negative, or 0? Discuss. So this area, this integral, represents this area under the x-axis. This would be considered a negative value, right? We are under the x-axis. We consider our areas negative. However, if you were ever asked to find an area enclosed, the area is always positive. So this area in green, even though the area here, using this integral, is considered negative, this area there is positive. And we would always consider areas enclosed by curves to be positive. Okay. So that's important to know. I'd like you to write an expression using one integral and thinking about this representative rectangle that you're summing up an infinite amount of them starting at A and going to B, but use maybe one rectangle to help you understand how you can write down a integral where we have height times width, but the height of this rectangle needs to be positive. The width is going to be positive because dx will be positive. We're going from left to right. But what expression can you use using P and M so that we have a positive height? So we can see that between maybe -1 and -3, this height is 2, just for that one. Okay, but no matter where we are between A and B, what would be an expression for a positive height in this situation? Go, discuss. So, if I take -1 and subtract -3 again, I get a +2, right? Now that -1 came from the top function. It's the y-coordinate of the top function. It's this p of x. The -3 came from the bottom function. Y-coordinate was -3. It was a greater negative value. Well, the distance between this top minus this bottom ends up being a positive distance. So we can write a very similar, if not the exact same expression for the area if my region is under the x-axis. We have a top minus a bottom height times our skinny width. And I'll go ahead and talk about if we are crossing the x-axis. And let's not use F and G again. Let's use P's and Q's. Would it be the same? Would an integral of a top minus bottom give us a positive area in green? It would. You can use values like 1 and -1. Think about 1 minus -1. It gives you that positive distance of 2. We definitely have a larger length here of this representative rectangle than 1. Really 1 minus -1, positive 2. It works. Now, each of these you can think in a macro sense. You could say, oh, let's take this positive area and subtract this negative area. And when I do that, I'll get that positive area in green. Sure. Or you could say, okay, I have this negative area. If I subtract a larger negative area, I'll get that positive area in green. Sure. I just actually think it's more complicated than if we just do, oh, that's my rectangle's height times width, boom, done. This is my height, top minus bottom, times width. It ends up being very simple. Okay, so go back to the first page, and on the bottom, we'll just make sure that we know in general, and it doesn't matter if you're to the left of the x-axis, the left of the y-axis. If I move this here, and we are talking about this region being in the second quadrant, does not matter, as long as you're going from left to right, okay? If we are talking about areas of regions between two curves, the area is always positive, regardless of location. This is just in the first page on the bottom. First page on the bottom, you have extra space. Always positive regardless of the location, and it will always be the top function minus the bottom function will give you a positive height times your very skinny width dx. I feel like I'm better standing up. Maybe because I'm going slower. Okay, infinite sum heights times width. Now, what happens if I flip-flop something? What if I did the bottom minus the top? Would we just get the wrong area, or would we get an area that is related to my actual area? Discuss with your neighbors. And look at your other situations with some of the numbers we used. If I did 1 and 3, but I did 1 minus 3. If I did, -1 and -3, and I did -3 minus -1. Yes, your instincts are correct. Those of you said it would be the opposite of the area. Okay, you'd get a negative area. Your heights would all be negative. Your widths would be positive. Okay, so keep that in mind. If you accidentally, while you're doing the problems that we're about to do, get an answer that's negative, most likely, though there could be other things involved, you just did not understand what functions on the top and what functions on the bottom. Okay? Okay. Now let's start doing some of these problems where we have regions enclosed by multiple graphs or a couple lines and stuff. And what's going to be very important is to understand how to get a general sketch of the region. I'm not going to jump straight into my integral. I could make a mistake. Instead, I'm going to sketch it. Now, I start with my sketches with my horizontal lines. X equals 0, x equals 1. Start there. You don't even have to put a y-axis down yet. Start with that. Because you know that you're between those two lines. I don't need the entire sketch of x squared plus 2. I just need a couple points between 0 and 1. Well, I don't need the entire y equals negative x. I just need it between 0 and 1. Maybe after plugging in 0, saying, okay, I have a point here at 2 and a point here at 0, you can say, all right, let's start here at 2, and maybe this is 0. And maybe then I'll put down my y-axis. And then if I plug in 1, I go to 3. And I have x squared plus 2, which looks like, a parabola. I have some sort of curve. This is not a perfect graph. I don't care. It doesn't have to be perfect. Then I have y equals negative x. So if I plug in 1, I get negative 1. So maybe I'm down here at negative 1. All I need is just a general understanding of what's going to be above the other function, what's on top, what's on bottom, and where our boundaries are, and we're ready to write down an integral, and we're ready to find the exact area. Okay, there's my shaded region. I'm ready to write down a representative rectangle, understand the height of its rectangle, and take an infinite sum of those rectangles. Height is our top minus our bottom. Width, small change in x. I now know that this area is from 0 to 1. I am taking an infinite sum of these rectangles starting at 0, going to 1. The rectangle's height, x squared plus 2 minus negative x. The width, dx. Now, for practice, I'd like you to evaluate this integral by hand. But also for practice, I'd like you to use a calculator to check your answer to make sure you got the correct answer. Okay, do it by hand, then check with a calculator. We'll be using a calculator more often than we're used to in this unit. Your test will be about half calculator, half no calculator. So if you don't have a calculator, go grab one now. And we just need to check our answer for this one. I want you to still do this by hand, please. Okay, remember, take the antiderivative, find the change in the antiderivative. Plug in 1, subtract 0 plugged in, boom, you get your answer. You get 17.6. Then, using your calculator, Math 9, plug your integral into your calculator. Make sure you get 17.6 as practice using our calculator. Do you need a calculator, Mr. Jindrisky? Don't plug it into y equals. We do Math 9 in the home screen. Anybody just need a quick reminder on how to plug in our integral into our home screen? It's okay if we do. I know a week off, we lose all calculus knowledge. It has to slowly be regained once we return. Okay. Next one. We got area between the graphs of y equals -1, y equals e to the x equals 0, x equals 2. Again, sketch. I'm starting with y equals -1, x equals 0, x equals 2. I don't know where the lines kind of extend to. Maybe they extend past it. I'm not sure. We know that this is probably the bottom. We have e to the x. E to the x starts at 0, 1. So I'm going to go ahead and put down my y-axis, my x-axis, y equals 0. And if I had 0, I get e to the 0, which is 1. If I plug in 2, I get e squared. E squared is something around 8 probably. And I can see this is the region. Now this all should be done without a calculator, and it all should be done just by hand and quickly. Don't want you to spend a lot of time sketching when it's not necessary. We then throw down a representative rectangle. Think about its height. Top minus bottom is the height of this rectangle. The bottom, though, not a graph. The bottom is just this line, this y equals -1. So the height is the e to the x minus the -1, or e to the x plus 1. Since I understand that height, I'll think about taking an infinite sum of these rectangles' heights times widths, starting from 0, going to 2, e to the x minus -1, top minus bottom. Go ahead and take the antiderivative and find this by hand, and then check with your calculator. What's the antiderivative of e to the x? E to the x. Yep, if that's right. Yep, looks good. Check with your calculator. Your calculator will give you a decimal answer, and then you're just going to compare it to the answer you got. after you plug it in. Antiderivative of e to the x is not log. It's e to the x. It's itself. The derivative of e to the x is e to the x. The antiderivative of e to the x is e to the x. Don't forget the antiderivative of your plus 1. So I get e squared plus 2 minus 1. That's e squared plus 1. I check with my calculator. And I see that's 8.389 when I have my calculator evaluate the integral. And then I check e squared plus 1, and I get the same value. Okay, so I feel pretty good about myself. Now, let's say I went straight into an integral, and I just assumed that the 1 was above the e to the x. Don't ask me why. Well, you would see if you went from 0 to 2 of 1 minus, I guess it's negative 1, negative 1 minus e to the x, and you flip-flop them, and now this is bottom minus top, you'd get the opposite answer. Okay, cool. I'd like you guys to do the sketch and the setup of the integral by yourselves. I'd like you to check then with a neighbor before you start evaluating it. Okay? Sketch, set up your integral, compare with a neighbor. Let's see if your integrals are the same, or your integral is the same as your neighbor's integral. Do not use your calculator to sketch. This can be done without a calculator, and it is expected of you to be able to do it without a calculator. Focus your attention on your straight lines. Those will help you set your boundaries. Check your sketch and your integral with a neighbor. You don't need to know exactly what 1 over x looks like. As long as you have 2 points, and if you did not include the x-axis or the y-axis, it might actually help you. X equals 1, x equals e, y equals 4. Let's just start with those. If I plugged in 1 over x, I plugged 1 into 1 over x. 1 divided by 1 is 1. So I know 1 over x starts at this point 1. Just going to say this is y equals 1. So I plug in e into 1 over x. I get 1 over e. Well, e is 2.7 around. So 1 over 2.7 is close to 1/3. 1/3 is less than 1. So maybe we're down here. And we connect it. I don't really need to know how to connect it, as long as I know that here's my region. Now, if after you kind of set up this region, you'd like to then throw down an x-axis and a y-axis, sure. But didn't need to. All I know is that this region is contained here. If we want to throw down a representative rectangle that we are infinitely summing up, the height of this rectangle is this distance, which is 4, minus this distance, which is determined by 1 over x. So in this case, the constant is above the function. So we would have an integral starting at 1 going to e of 4 minus 1 over x that we can evaluate by hand and then check with the calculator. Please evaluate this by hand. Check your answers with a neighbor and with your calculator. What is the antiderivative of 4? What is the antiderivative of 1 over x? Power rule does not work for x to the negative first. It is the only power that the power rule doesn't work for. Every other power used the power rule. But for 1 over x, the antiderivative is log absolute x. We then plug in e and 1. We need to know what the log of e is. We need to know what the log of 1 is. It was tested on the last test and on previous tests. This is e to the first. This is e to the 0. The log of e to the first is just 1. The log of e to the 0, or the log of 1, is 0. You get 4e minus 5. Okay. The sketch. The understanding of the region being the most important part of the question. This part, it's assumed that we know how to go from here to here to here to here to here. That's assumed that you know how to do that. Okay? That shouldn't be the hard part. It's starting from here and getting there. That's the key. Or really starting from here, sketching that, and then creating your integral. Lots of blue right there. All right. Extra layer of difficulty. What if you're not given the x boundaries all the time? And we won't always be given the boundaries, the x equals lines. The situation might be a basic example, but the next two are definitely more complicated. Okay? We have y equals 8, x equals 0, and y equals x cubed. So if I start at x equals 0, I know y equals x cubed has the point 0, 0. And I know the y equals x cubed looks something like this around that location. Okay, so maybe if you want to put down an x-axis here, sure. But you should be able to tell from your first couple graphs that this is our enclosed region. And here is our representative rectangle. Its height is 8 minus x cubed. 8 is this distance from the x-axis all the way up here. The x cubed distance is right here. Subtract the 2. That's the height of my rectangle. All right, so I'll take an infinite sum of those heights times the skinny widths. So I got 8 minus x cubed, dx being the width. I know I'm starting from 0, but it was not given to me where I end. And the key is this location right here. That intersection is where the region stops being contained. And I need to find that intersection. Now, it's pretty obvious to just kind of see, and since you're familiar with x cubed, you can kind of just figure it out. But let's say you're not, and for the next couple, it won't be obvious, okay? We need to find the intersections to find our other boundaries or all of our boundaries. Now, how do we find intersections? Well, it's the x-coordinates for your graphs that produce the same y-coordinates. So when do we have shared points? Set your equations equal to each other. See when your x-coordinates for a given x-coordinate produces the same y-coordinates. Set equations equal to each other. So we get x cubed equals 8. Take both sides to the 1/3 power. We should know that 8 to the 1/3 is 2. Cubed root of 8 is 2. So that's why this is 2. The rest is stuff we should already be able to do. You can check with your calculator. Questions? Next problem. We're not given any lines at all. We're just given 2 graphs. So, I don't even know, where do I start and end my sketch? Because I do not know where to start and end my sketch, don't sketch yet. Don't jump right into sketching until you have a very good understanding of where we're starting, where we're ending, and where we need to pay attention to on a y and x axis. So find your intersections first. That will determine your boundaries. That will help you sketch. So we set 2 minus x squared equal to x. And we solve. We got x squareds and x's in an equation. Move everything onto one side of the equation. Set it equal to 0. Factor to solve. Okay, go from there. Go, do the rest of the problem. Once you find your intersections, now you know where your graph is contained. Actually, I'll help you out here. You'll do the next problem. You know your graph is contained between -2 and 1. Maybe I draw a y-axis, maybe not. Maybe I just think about -2 and 1. And if you plug those points in here, you know where the y-coordinates are of their intersection. They will intersect at 1, 1, and at 2, -2. So that's kind of the start and the end. We know a line. Y equals x. We'll go through the origin. So that's good. We know what that looks like. There's multiple ways to know that the parabola will be over your line. You have 2 minus x squared. Minus x squared means that the parabola is opening downward. So that's one way to know that you're connecting these 2 points with a downward parabola. Another way to know that the parabola is going to be above your line is use some points in between your intersections. Just like when we're finding when things are positive or when things are negative, if we found all of the intersections, we know between intersections, we will always be either above or below, just based on one test point. If I plugged in 0 into 2 minus x squared, I get 2. 2's up here. That means I know definitively, so long as I found all the intersections, that the parabola will be above the line everywhere on this interval. And here's my shaded region. Here is a representative rectangle that I'm summing up. Its height is 2 minus x squared minus x. Now, I do not want you to evaluate this integral that you're about to set up by hand. It'll just take too long. Instead, let's just set it up. We're starting from -2 to 1. We're taking infinite sum of these heights times the widths. Heights, 2 minus x squared minus x. The widths, very small, dx. And plug this into your calculator, and you get 4.5. Okay? Now, ready, set, do the next one by yourself. And I'll be coming around to make sure you are doing it. Put everything on the one side, factor to solve. Make sure we understand which function ends up being above which function. Which one's on top, which one is on the bottom. Don't just assume, don't just think that it's going to be the same thing as the last problem we did. You can either just pick a test point, compare the two y coordinates, or understand that it's a positive x squared plus 2x plus 1. So positive 2x squared, positive x squared means we're opening upward, which means it's going to be below. Or you plug in, 0. If I plug in 0, I get 1 instead of 3. Multiple ways to know that your parabola is under your line. Knowing the parabola is under your line, you know the top is the line, the bottom is the parabola. Top minus bottom is the height. That's 3x plus 3 minus the entire x squared plus 2x plus 1 function. Make sure you subtract the entire thing. Use parentheses. Common mistakes are not subtracting the entire thing. Then, if you'd like to, you could even simplify things. You got negative 1 to 2 of negative x squared. That'd be 3x minus 2x, which is plus x. And 3 minus 1, which is 2. Okay? These are equivalent. And after we do that, this is why we want to write it with one integral, because if you were to do this by hand with two different integrals, it'd take you a lot longer than doing this by hand. Oh, thank you. Okay. What if our graphs intersect at more than two locations? Discuss with your neighbors what you would do to find this shaded area in green between F and G. Go. Run away, Mr. Do. All right, if we said use two integrals, you're correct. If you go to A to B, the top is F, the bottom is G. So there's top minus bottom from A to B. But from B to C, top and bottom changes. Now the top is G, the bottom is F. Okay, so I need multiple integrals. But actually, I could do this with one integral. I can do this with one integral from A to C. Discuss with your neighbors. Try to come up with an expression that I could put in that integral so that that area is the correct area and is the same as this here with two integrals. Any ideas? Nobody? Nobody has any ideas? You don't think you can? Impossible? It's possible. No.
Absolute value.
Absolute value is correct, Mr. Radu. That's a great idea. Anybody else came up with that and just not confident enough? It's okay, next time. Thank you for thinking of that. Why? If I did F minus G, I get the positive height, right? F minus G, that's positive height for there. But what happens if I get F minus G here? What is F minus G in this situation? It's the negative height. If I just want all positive heights, well, I need some sort of operation that takes positive things and leaves them positive, but takes negative things and takes them and turns them into positives. That operation is my absolute value. And it doesn't have to be F minus G. It could be G minus F, right? It would just, if these would have been negatives and these are positives. All it is, it's just the absolute value of either minus the other. And actually, for all of the previous problems that we've done, we could have done that. We could have kind of skipped the sketching part, skipped the messy part. If we knew the boundaries, we had a calculator, you can use an absolute value and do either minus the other over your interval, regardless of how many intersections, and boom, you get the right answer. But we're not going to be able to do that for all of the questions that we're going to have, obviously. So be prepared to do the process that we just did by hand. Okay. These graphs, this cubic and this quadratic, will intersect at multiple locations. I have what it looks like, but let's just pretend like we don't know what it looks like. What would I do first? Same thing I did with the other problems. I would attempt to find the intersections first. And to find the intersections, I'd set the two equations equal to each other. Now, I actually can solve this, factor and solve this by hand. Let's pretend I didn't, but I was able to use my calculator. Can you find the intersections of two graphs? Yeah, you can. Second calc intersect. So graph these really quickly. See what they look like. Find the intersections. Second calc, intersect, enter, enter, enter. There's 3 of them. Question asked me to write an integral without an absolute value. So I needed to find the intersections, needed to see that they're actually at -2, 0, and 2. This is something that we could have found by hand. And understanding what's on the top and what's on the bottom between your intersections. Since I know that the red graph is F and the blue graph is G, I'm just going to use F and G rather than rewriting it out multiple times. I'll go from -2 to 0 of F minus G, and I'll add the integral from 0 to 2 of G minus F. Okay. All right, 2 more. Different type of question, though. A little bit more complicated. Another curveball being thrown at you. Now, we have a region here. We already evaluated this region. Okay, x squared plus 2, x equals 0, x equals 1. Y equals negative x squared plus 2. Looks something like this. Okay, this is the first one that we did. We found that the area was an integral from 0 to 1 of x squared plus 2 minus negative x. And we found that value is 17/6. Okay? That's just what we've already done. The question is, find the value k such that x equals k splits up the area of the region into two equal parts. So we have some line, x equals k. Okay? This line needs to be placed somewhere so that the area to the left of the line equals the area to the right of the line. I'd like you to discuss with your neighbors, maybe using an integral or multiple integrals, some sort of an equation that will use k that we could potentially solve to find k. Go. Okay, ideas. What do you think, Mr. Strauss? Great idea. Other ideas, Mr. Pittman?
Setting up an equation where the integral from a to k function is equal from k to b.
So that is typically what students come up with, is they say, okay, if I go from 0 to k of the top minus bottom, that has to equal the integral from k to 1. So the area to the left and the area to the right have to equal each other, right? So that's what typically we think about. Our first instincts is that the area to the left equals the area to the right. However, I got two integrals that have to be plugging in k in multiple locations. Mr. Strauss came up with a very ingenious way. You went from k to 1? Yeah. So I would probably go from 0 to k, Mr. Strauss, because I know when I have to evaluate this integral and I have to plug in 0, simplifies things tremendously. So this works, sure. Great, great thought. Or instead, we already know what the area is. So the integral from 0 to k will equal 1/2 the area that I already found. Okay, everybody make sure you have that down. Okay, now hold on. We're not done yet. We need to find k. Now what do? Do I guess and check and start plugging in different k values? No. How can I find the exact answer? Take the antiderivative. Evaluate this using the fundamental theorem of calculus. So, write a little note here. Use FTC. Take antiderivative. Plug in k in 0. Okay? This is 1/3 x cubed plus 2x plus 1/2 x squared. Find the change in that from 0 to k. we get this equation, 1/3 k cubed plus 2k plus 1/2 k squared minus when I plug in 0 everywhere, we just get 0, and that equals 17/12. We just created an equation that no longer has an integral. Make sure you guys got that down. Now, do you think we can solve this by hand? No. Immediately looks tremendously messy. Okay? How can I solve it if I can't solve it by hand? Our friend the calculator. Okay? Now really quickly, what do? We graph y equals the left side and y equals the right side. And we find the intersection. Graph, second calc intersections. Just like finding intersections of two graphs just in general. I get 2 points. I got an x and a y. Which one's my answer? Well, you tell me. It's the x. Y is 17/12. So we found x is 0.588. Some things to notice. Our answer should make sense. It needs to be between 0 and 1. We can kind of see that it's going to be to the right of 0.5 based on the shape of our region. Okay? All of these can help you make sure you get the right answer. Thank you. Homework's out of the book.